Welcome to Real Civil YouTube channel. In this video, we are going to study how to calculate or calculation of seismic design force. We are going to calculate the seismic design force by using equivalent static method. Okay, this is our second problem. First problem we have already covered. You can see in the description box. This is type 2 problem. Data is given in terms of some different format. So how to solve those problems we'll see. First of all, we are going to read the problem. So this is the problem statement. I am going to underline the important points. Okay, here consider a 4-story reinforced concrete office building. Okay, so 4-story office building is there, reinforced concrete. As shown in figure, I will show you the figures. The building is located in Shillong, seismic zone 5. The soil conditions are medium stiff and the entire building is supported on the raft foundation. The RC frame are infilled with brick masonry. The lumped weight due to dead load is 12 kN per meter square on the floors and 10 kN per meter square on the roof. The floors are to cater for live load 4 kN on floors and 1.5 kN per meter square on the roof. Determine the design seismic load on the structure as per the new code. So this is the entire problem statement. This is the plan of the building. Here you can see the X direction and here you can see the Y direction. In X direction there are 4 bays and each bay is of 5000 millimeter, or we can say 5 meter. So each of is 5 meter. Okay, and if you see the y-axis, here you can see these are the 3 bays. Again here they have given 3 bays at 5 meter or 5000 millimeter. Okay, next thing is elevation. Here you can see this is first story, this is second, this is third, and this is the roof. Okay, so we will solve the problem. Okay, so let's start with calculation of the seismic weight. Okay, let's start with seismic weight calculation. So in seismic weight, we know that we have to add the dead load and live load. We will calculate for typical floor and for the roof separately. Okay, so here if you see, typical floors are nothing but this is, we can say W1, this we can say W2, this we can say W3, and this is W4 is our roof. Okay, so we'll calculate W1, 2, 3 and then W4. Okay, now first of all, for typical floor, dead load is, here you can see in the problem statement, the lumped weight due to dead load is 12 kN per meter square. Okay, on floors and 10 kN per meter square on the roof. Okay, that is the only thing. So dead load for a typical floor given is 12 kN per meter square, whereas dead load for the roof is given as 10 kN per meter square, 12 and 10. Now let's check out what is the live load. So here live load given is 4 kN per meter square. So before going into the calculation, there is one clause that we need to study. Okay, here we are going to solve all the problem by using IS 1893 2016. This is the latest code. Okay, I'll just open for the live load what is the clothes. For this you need to turn to table 10. I will just zoom in so that you can read the clause. Okay, I will just tell you what is given in this clause. In this clause, the clause says that for the roof live load there is no need to consider. That means it should be zero unless and until you have any fixed equipments or instruments on the floor, on that roof, then you can consider. And floors for other floors live load should be, here that they have given the table 10 percentage of imposed load to be considered in calculation of seismic weight. So they said that if your live load is 3 or less than 3, you consider 25%, and if it is greater than 3, you consider 50%. So simple, our live load is 4 kilonewton per meter square. That means we have to consider 50%. So for all other floors, live load is 2 kilonewton, and for the roof, live load will be equal to 0. So we will put this value back to our calculation page. Here, as I told you, live load here will be equal to 2 kilonewton per meter square, and live load here it will be 0. Okay. So typical floors are W1 equal to W2 equal to W3 equal to. So yeah, the values of dead load and live load are given per meter square. Here you can see common unit is per meter square. So you have to multiply it by area into dead load plus live load. Okay. So plan area is, here you can see our plan area is, this is 5 meter each. So 5 into 4, so it x is 20, and here 5 meter each, so y is 15. So 20 into 15 is our area. So we'll write here 15 into 20 into, here dead load plus live load. For typical floor, dead load is 12 and live load is 2. So if you do this calculation, you will get the value 4200 kilonewton. And now W4, that is our roof. This is W4 roof. This level is roof level. Okay. So for the roof level, dead load is 10 and live load is 0. So W4 is equal to area, again same, 15 into 20 into 10 plus 0. So this value is coming out to be 3000 kilonewton. Okay. Now total seismic weight of the structure. Here total seismic weight of structure, capital W, is equal to summation of all the weights, that is equal to 3 times 4200 plus 3000, because W1 plus W2 plus W3 plus W4. This is what we have done here. So it is coming out to be 15,600 kilonewton. So this is our W. Remember this value, we will use it in our further calculation. Okay. Now let's move towards the fundamental time period. Okay. So fundamental time period. So how to calculate fundamental time period? So for this, we need to go to the code again. Here I have downloaded the code. So okay, I'll just zoom in. Okay, so if you refer to this clause 7.6.2, here you can see they have given how to calculate time period. They have given three conditions. This is condition A. Okay, this is the condition B, and this is the condition number C. If you read our problem once again, you will come to know that in our structure there are infill masonry infill walls. Okay, so first is without masonry, second is structural wall, that is also not present, and third is for all other buildings. So we will refer this formula of time period. Okay, if you look at closely, here you will see TA is equal to 0.09 h into root d, where h is height of the building which is required in meter, and d is the base dimension. Okay, along the considered direction of earthquake shaking in meter. Means what? In plan, as I show you, there are two directions, that is x and y. Okay, so if you are calculating for earthquake in x direction, you have to consider the x direction, and for y direction earthquake you have to consider y. Okay, how to calculate? I will show you. So let's get back. Fundamental time period. So we are considering the earthquake in x direction. We are considering the earthquake in x direction. Okay, so the formula is T is equal to 0.09 h divided by root d. So that is equal to 0.09 into h is the height of the building. Height of the building you will get here. Total height of the building in meter. You have to add this 3200, 3200, 3200 and 4200. Okay, that is in millimeter. We are calculating in meter. Hence, after calculating, we will get 13.8. It is in meter. Divided by base dimension, root d, or d is base dimension in x direction. So just go to the plan. In plan, check the x direction distance from this to this. So we know that this is 20 meter. Okay, so we will use here d as a base dimension 20. Okay, if you are doing for y direction, then your d will be this much, that means 15 meter. So it depends upon in which direction you are calculating. We are calculating for x direction, hence we are consider 20 meter. So we will get the time period here. Time period is 0.28 seconds. Remember this value also. Okay, now let's move towards our third part, that is base shear VB is equal to AH into W. We have already calculated W. You can see this formula on, I'll show you, that is on page number, I think, here. Here you can see this formula, VB is equal to AH into W, where VB is the base shear, AH is horizontal acceleration coefficient, and W is the seismic weight. We have already calculated W. Now our job is to calculate AH. So how to calculate AH? For that, you need to go here. I'll zoom it. So 6.4.2 is the clause. AH is equal to Z by 2 SA by G R upon I, or you can write Z by 2 into SA by G into I by R. Okay, so let's back to the calculation page. Okay, now we know that AH is equal to Z by 2 into SA by G into I by R. So let's calculate one by one. Okay, this is very simple. So Z is your zone factor. In our problem, they said that it is zone 5. Okay, so for zone 5, how much is the value of Z? So again, you need to go back to your code. Okay, for code, uh, the page number is, I'll just zoom out. You have to come to the table number 3. In table number 3, you can see zone factor. So in our case, zone is 5. So zone factor we have to consider is 0.36. Okay, first of all I will explain everything and then I will write. Okay, or you can see the map of India. Here you will come to know the zone, and from that zone you can take the value of zone factor. Okay, or you can go to the appendix also, where they have given some cities and their zone and zone factor. So these are the different ways you can get your zone factor. Okay, next we will get importance factor. For the importance factor, you have to come to table number 8. Okay, so for that we have to see our problem. So it is an office building. So importance factor for the office building we have to see. Okay, okay. So importance factor. So if our building is school building, government office building, then lifeline structure, then importance factor is 1.5. Residential or commercial it is 1.2, and for all other building it is 1. Okay, so here we are considering the importance factor as a 1. Okay, so our Z is 0.36, our I is 1. Okay, let's find out what is the response reduction factor. Okay, so for response reduction factor you can just go to the next page and table number 9. On table number 9 they have given response reduction factor. Okay, our building is special moment resisting frame, SMRF. Okay, they will mention which type of building is there, and based on this our response reduction factor will be 5. So R is equal to 5. Now only thing we have to calculate is SA by G, and for SA by G we have to again go back here. This is very important. Now I'll just adjust the page. If you remember, in our problem they have given that soil type is medium or steep soil. So our soil type is 2. Okay, now we have to find SA by G. So on this page you will see these two parts, A and B. Okay, the B part is for response spectrum method. Okay, we are not looking this because we are following equivalent static method, and we will see this. only, because our site is medium steep soil. Okay, if you here we need to see our t. Our t is we have calculated, which is 0.28. So this 0.28 will come here, 0 to 0.55. So t will be 0.28. Okay, so that will lie between this. So for this, SA by G is 2.5. This is how you have to read. Okay, now we have all the values. Let's come back to our calculation page. Okay, so Z is 0.36 multiply by divided by 2 multiply by SA by G is 2.5. Importance factor is 1 and response reduction factor was 5. If you solve this, you will get AH is equal to 0.09. Okay, now you have to put this value in this formula. So VB is equal to AH, that is 0.09 into W. W is 15600. So you will get the base shear 1,440, 1414 kilonewton. Okay, so this is how we calculate the base shear. And the last thing which is remaining is lateral distribution. Lateral distribution of base shear, or lateral distribution of the load, okay, on the along the height of the structure. Now for that, we are going to refer, or we are going to create one table. In that table there is a story level. Okay, second is weight, then height is there, then wi hi square is the second, then wi hi square divided by summation of wi hi square. Okay, and then lateral force. Lateral force in x direction on each story. Okay, I'll just complete the table. Okay, story level, we know that our structure is 4 story. So 4, 3, 2, 1. Let me just finish. Okay, so weight here on the final floor is 3000. Here it is 4200. Here also 4200. Here also 4200. Height, we have to put the height in the reverse order, means final story is at 13.8. Third story is at height of 10.6. Then this is 7.2 and this is at 4.2. It is in meter. If you just go and see elevation, you will get this value. Now I am not going to do the calculation. Here what you have to do, wi hi square means 3000 multiply by 13.8 square. Do it. Similarly here 4200 multiply by 10.6 square, 4200 multiply by 7.2 square, 4200 multiply by 4.2 square. Okay, so at the end you have to do the summation of all. Okay, you have to add these values, and then here I am giving you WHI square means this value divided by the total value. So you will get here 0.424, 0.350, 0.171, and 0.055. You can refer our video also. You will get the calculation, our previous video in which I have explained how to calculate this. So I will just give you the values 246 and 79, and this is the lateral load distribution. Okay, you have to just show it. Okay, okay, and this final flow rate is 611, then here it is 504, then here it is 246, here it is 79, and this is our base. This is how we do the calculation of the lateral load distribution with height by static analysis method. Okay, if you have any problem you can comment me. If you feel difficulty in this table you can refer our previous video in which I have explained it in detail. Still, if you get any doubt you can contact me, you can comment me, I will surely explain. Okay, so thank you so much for watching the video. Please like, share, subscribe the Real Civil YouTube channel. Thank you so much.